Afternoon, everyone, and thanks for joining today at the Timber Design Society webinar. So today we talk about timber structures, some case studies, and it's slightly different from the usual ones. We're talking about more modern, new geometry and pushing the limits when it comes to timber. And for this, we have Peter Corbett joining us today. Before we start the presentation as such, a quick thank you to our sponsors. You can see them at the bottom of the screen, and obviously the Timber Design Society Committee, who is supporting this initiative. Some quick news from the Timber Design Society. As you probably have followed over the last few months, we are co-organizing the New Zealand conference, or the international conference in New Zealand on the timber bridges, which will be held on the 29th of June to the 2nd of July in Rotorua, which is a unique opportunity to learn about timber bridges. And we also have now 5 teams who will be competing in a bridge competition. So if you're interested in timber and or bridges, I recommend you join the conference. You can see the member rates on the screen, and as a TDS member, you get $100 off. Also, our research scholarship applications are out there, and the deadline is on the 13th of June. So if you are a researcher working in the timber space, that might be something for you to apply and get some pocket money out of it. Also, the next TDS webinar will be on the 15th of May, and we're going to talk about timber bridges, obviously. And we have Peter Robinson from Papua New Guinea Forest Products, who will present on the projects they have been working on and where they have delivered either the plywood decking or other timber members for those bridges. But back to our presentation today with Peter Corbett. So Peter is a design lead structural engineer at Becca in Wellington, who has moved from the UK, where he has run with his partners a very successful practice. And his passion, obviously, is timber design and also innovation. And he has worked on several high-profile structures in the UK and in other places, and he will showcase some of them today. And the design process behind those structures is obviously applicable to the New Zealand reality as well. And his presentation will move away from the traditional glulam or timber beam and post and columns, and he moves more into other, more efficient structural forms, which really underlines the versatility of timber, where you can curve and bend and use the timber where it's best at. So with that, I pass over to Peter, and I'm really looking forward to this presentation from him.
Okay, thank you very much, Daniel. Sorry, I was just finding my screen. Okay, so hopefully that works for everybody. Is that right? Do we have the right? Just double check. Yes, okay, good. Yes, I can see the confirmation there on my screen. Good. Yes, good afternoon, everybody. Thanks for joining, and thank you for that introduction, Daniel. Yes, that's. I think you summed it up nicely. I'm going to talk today about a subject which has been a pretty key interest and driver for me throughout my career, which is this relationship, this important relationship between geometry and structural design. And I hope by the end of it, I'm not entirely sure who exactly the audience is, but to the New Zealand audience at large out there, I hope to convince you that you will also find it as interesting and important as I do. So I'll move through the slides here, and I mean, Daniel, you summed this up already, but I discovered my passion and interest in timber from my very first kind of structures that I was designing in London, which happened to be with timber. And I think I'm not alone in experiencing this, but you kind of get a bit of a bug, which you can't really shake. I mean, as engineers, we tend to be generalists, and we have to be comfortable in all materials, and on behalf of our clients, we need to be selecting, the most appropriate material for the right place. But yes, I have to admit I do have a bit of a first love of timber, and so we always, since then, I've always asked myself when I'm starting on a project, can we use timber? Is timber the right choice? And that's really where the design kind of process starts for me. So yeah, for many years I was working in the London area, all around the UK and abroad, and more recently I've moved to Wellington, where I work with Becca, and I'm helping drive forward and provide a focal point really um, for our teams of engineers for all things timber. And yes, I think, like many practices here, we've really had we've really been part of this kind of renewed interest in timber, and in particular mass timber, over the last decade or so. And there's some very impressive projects I've come across and been learning about since I've been here, and you can see some of them kind of on the screen here. Really a wide variety of structures, aquatics, educational, airports, from some pretty special kind of one-off structures to more kind of everyday and pragmatic structures there too. So moving back to today's focus, so the team that we created in back home in the UK, we, as well as trying to make our structures ensure that they were safe and standing up and met the brief and all the rest of it, we also had a bit of a manifesto, which I put up on the screen here. We affectionately referred to them as our 3 E's, and these were our kind of guiding principles as we kind of dealt with a whole range of projects kind of across the board. There is a longer kind of backstory here, which I'm going to try not to get diverted into, to do with Plato and his solids, his five solids, and his kind of transcendental truths, if you like. But I'll just summarize it here, what it meant for us as kind of engineers. As engineers, we're looking for efficient structures. What's the best way from getting from A to B to span across a space, or form a certain kind of function within this building, and that's really to do with the form and the material, how we're analyzing it and how it performs. But it's also, I think, important, and particularly with structures which are timber, where we like to very often expose them as a feature to the finished building, is what do they look like? Is it elegant? Is it elegantly proportioned? Do we have the right system, the right details, and the right amount of material in the right place? And then, yeah, the economy, not only in terms of money, but also in terms of carbon. Can our clients afford this? Can the planet afford this building? That's very important if we are to not just have a building which can be designed, but one that can be built and afforded to be built as well. And this idea of efficiency, I think this is a little extract from it's quite long on the tooth now. It's a design study from a long time ago, but looking at the different relative structural performances in terms of the carbon footprint of different structural forms, all with the same grid. And you can see here how arches, and also to an extent trusses, can perform so much better than traditional beam and post. And that's just one example of what we mean by what we refer to as structural efficiency. And yeah, most of my slides are actually images, but I'm starting off with a few text-based ones here. Loads of different ways of kind of categorizing structures, and the choices we make in the as designers at the early stages of our kind of project, as which route do we want to go down here. And this is a way we used to think about it, kind of relating in a way to the human body, a kind of skeletal structure or a framed structure, which is your traditional kind of beam and post, and then the cladding or the skin would be perhaps non-structural and added on afterwards. However, that's not always kind of necessary, and timber, I think, in particular, although this is in a way kind of material agnostics kind of point, you can actually make the membrane or the skin your structure too. And yeah, so that's I think an important thing to remember. And then, yes, these different force systems that then get set up depending on which geometry you choose. A beam and post structure where things are meeting, close to right angles. These tend to have kind of relatively high bending forces, which is not always the most efficient way of getting from A to B, whereas either an arch or a catenary perhaps, or a combination of the two, you've got direct stresses, direct forces, and you can actually have much less structural material to span across a space with these kind of systems. So I'm going to start off just to try and illustrate this kind of relatively abstract point with a case study. It's modestly scaled kind of project in the south of England for a community centre. And this is the early architect's model that you can see here, and a fairly traditional kind of series of goalposts spanning across. But what you can see is that each goalpost, whilst it's a straight line, is also at a different angle, and the form that's then set up over the top of this, yeah, that's as a structural engineer, that's really interesting, and I'll come on to more detail of that shortly. But this shape, and there are a whole host of different shapes, but I'm going to pick on this one in particular, this form of doubly curved surface, and in particular something which is referred to as anticlastic curvature, where the center point of the curvature in the two different axes is on opposing sides of the surface. Yes, otherwise known as the hyperbolic kind of paraboloid. Now, with form finding, there's loads of ways of generating form. Often you might want to do a grasshopper script attached to Rhino, or a similar kind of form finding process, or you can, in the photo here, dip some bent wire into some soap film and create and see what comes out. This is a minimum energy surface. It's the and the soap, by some kind of magic trick, just finds this minimum energy surface. And for those interested, yeah, so I'd encourage you to look into these further, because this is a very, very interesting area of design. Now, I'm going to talk about the hyperbolic paraboloid, but it's not I'm using it as a case study, as a kind of springboard. There's actually loads of other different of these shell forms around, and timber being this kind of amazing versatile material that can be shaped and sculpted into different kind of products and forms, can be used for most of these. And you'll find examples going back, not just recently, but going back kind of decades and actually centuries, looking at how these different shapes have been formed over the different ages. This is a little extract from an old 1950s paper from TRADA, who are the Timber Research and Development Agency. in the UK, and there's some very interesting kind of library they have for these kind of forms. So it's kind of a pretty interesting thing that we can create a doubly curved surface from a series of straight line generators. So you can see on the left here, figure 1, if you draw lines parallel to the edges of this surface, they're all straight. But if you go between the opposing corners, they're curved. And the shape, which we started off with looking with the model, has 2 opposing high corners, and the other 2 corners in the opposite sides are low. Just so happens that sets up this geometry. So a bit of a magic trick there. And don't just take my word for it. If you have some balsa wood and some glue, you can try this at home. How these kind of straight lines create this double curved surface. Now that's really interesting as an engineer, because you can see here in the images that if we track a line between the 2 opposing low corners, we have an arch, and if we track a line 90 degrees to that, we have a catenary, and both are very efficient structural forms, as we started off by talking about. And these, fairly classic shapes you can see here are been kind of tried and tested by engineers and builders over the centuries. Now, how to form this, how to make this out of timber, how to fabricate it. This was a bit of a DIY project going back many years now. I was quite interested in boat manufacture, but very often buildings are kind of flat surfaces and rectilinear shapes, whereas boats and anything that moves, really, people are much more interested in making things which are curved so they can kind of slip through the water. We made this out of 3.5 millimeters plywood, which could just about be persuaded into double curvature at the bow and the stern. What was kind of amazing is that the plywood started off by being relatively flexible and floppy, and as soon as you curve it into this shape, it goes tight like a drum. So it was became much stronger, not by adding material, but by and much stiffer as well, but by generating this curvature. Back to our community center. The question is how to do this at scale. Again, going back to this 1950s Trada paper, these shapes were very often laminated on site with strips of timber going in 2 directions, and then either glued or nailed, or both, kind of laminated together on site. Now, that's quite a difficult thing. Many reasons. First of all, you're introducing glue on site, and all the vagaries of the weather and quality control makes that somewhat complex sometimes. But also, just it's quite a manual process and takes a while. And you've also got to build 2 structures: the temporary structure to provide the kind of propping and generate the form, as well as the permanent structure to create your shell. So how can we do this using today's construction techniques? LVL is, we have something called Curto Q over in Europe, but you have something very similar over here using pine. This one uses birch, but it's a similar kind of product, a kind of more contemporary way of creating these panels would be to use these sheets of LVL. So you're kind of taking something that used to be done on site and doing it off site in a controlled environment in someone's workshop, which has got to be a good thing, right, in terms of reducing risk and speeding up construction times. So I mentioned before this issue with shell structures is having to create two structures, your temporary structure and your permanent structure. On this particular project, our architect had already created a series of portals on his initial model, and we decided to use these as the kind of permanent formwork. We like to define the geometry up in the air, and then on top of that we laid our red LVL panels, which were our catenaries, and then on top of that our blue LVL panels at 90 degrees to that, which were our arches. And that was a relatively straightforward process of layering up the elements one on top of the other. But it still kind of appeared complex on the drawings. So we made a little model to talk to our fabricator over to show that it's how we thought it could be built. And if we can build it ourselves using kind of balsa, I think that's a good starting point to seeing how we can build it in real life on site. So we've got a number of different load paths here and choices which the force on this roof can take, how to get down to the foundations. We've got beams or ribs going across, and we've also got LVL panels on top at two different angles, creating our arches and our catenaries. Which way will the load go? Well, it's can be a little bit uncertain, and the process of answering that question is can be answered a number of different ways. One of those is using analytical software, in this case Oasis GSA, to model our shell and our ribs and work out the forces and deflections, and it all depends on forces like to travel the stiffest route, and it depends what relative stiffness you give these different load paths. That is an interesting subject to talk about, but I'm not going to talk about too much about that just now because we'll run out of time, but I'll try and come on to it later again when we talk about some of our other structures. Now, wherever you have an arch or a catenary for that matter, you also have these kind of lateral kind of thrusting forces. And for this particular project, we decided to create these steel tripods in the two low corners, which would take those thrusting forces down to the foundations. I have some construction images here. I think, yeah, they weren't actually beams. We called them ribs because they were more slender than they would otherwise have need to be if we didn't have this shell helping them out on top, which was just created quite simply by laying these sheets of LVL on top at 90 degrees, and these were screwed down into place and to hold them and make sure the shell acted all together compositely. And you can see here, it's a fairly kind of low tech, kind of community type kind of project, but this kind of angle kind of shows the geometry which is set up, this quite gentle curvature. Now you can see the guys on site there. People who work with wood are called joiners, and they're called joiners because wood is all about, or timber is all about the joints, and the question is how to connect these elements together in the best way. And I think this is of interest to anybody working with timber, I think. But what can we learn from the furniture industry, where joints are often kind of concealed and or at least kind of quite elegantly done. And in this case, we have these concealed glued in rods, which were pre-installed into our column heads, and then they were used to fix these kind of the beams down. And you can also see, I think when you get into these shell forms, yeah, we find that the edge beam along we need this edge beam to stiffen up the edge and create a load path, and we did that on top of our diaphragm and concealed within the architectural finishes. And here, this is the final kind of jointing detail. So it was a quite important one to get right, given this glazing band around the edge. Now, I mentioned earlier about some of the analysis that we'd gone into this roof. So I remember going to a long time a presentation by somebody called Bill Addis, who talked about the evolution of structural analysis over the 20th century. If you go back to the mid 20th century, people were building scale models in labs and measuring deflections and strains, and then scaling that up into the full scale structure. And nowadays we use a lot of finite element and computer analysis. But how do we know that they're right? And I think I'm quoting him, paraphrasing him correctly by saying, yeah, you're testing reality with a physical model, but you're only testing a certain set of equations which have gone into the finite element model in the first place. So you've got to be very careful with this. But what it does do is this little sequence here kind of shows one of the critical failure modes that we were interested in this shell, which is this quite shallow vault, was actually the non-linear behavior of buckling effects under compression of this relatively thin shell, which needed to span the space is about 10 by 10 meters on plan, about 13 meters across. So the LVL was 2 layers of 33 millimeters, if I memory serves me correctly. So it's quite a relatively thin shell for a span like that. But this was an important thing to get right, was the buckling characteristics. Now, my next case studies are a series of chapels, and all these projects actually owe a large amount to a great relationship we had with an architect called Nicholas Popel, who was a great friend to David Tasker and myself. And we together designed a series of chapels with him, and they all used timber in various forms. The first one was this, again, quite modestly scaled chapel in Canterbury. And this was the initial model. We have the main chapel space on the right there, and then the community room, which is 5/8 of the size on the left hand side. And we can see quite interesting kind of roof geometries. If you go back over the ages, there's some really great structures have been used for these different religious buildings, and yeah, the arch and the dome feature very heavily. Those, yeah, going back centuries, they tended to be done with masonry. Nowadays, that's quite kind of labor expensive to do, and it's not really not really the done thing anymore, and especially not here in New Zealand, actually, for obvious reasons. But timber and the way that it can be made into these different products offers a good opportunity to look at these shapes again in a new contemporary way. This was some of the early engineering sketches, which we were explored with the architect. So the question is how to build this roof. It's quite a modestly scaled chapel. It's about 9 meters by 7 meters across. But it was an interesting design kind of process, and we were very interested in the use of these SIPS panels, plywood face layers, and a rigid insulated core to create this kind of lightweight panel, which could be pre-made into different shapes and then fixed together. And this was actually a special panel that we developed with somebody called Gordon Cowley in the UK, who is a who was one of the kind of leading designer builders in the UK, and somebody whom we had a lot of respect for and worked with a lot over the years. And he made up these 200 deep panels for us in his workshop, and we tested them and got some kind of stiffness plots, which we could then correlate to our finite element analysis. You can see up here on in the right hand side, using a special shell element, which is actually used in ships, actually, for ship hulls, where they are also interested in these kind of lightweight systems. As you can see, this is not moving hardly at all. It's such a stiff shape, and it's a small amount of movement, less than, well, by prediction, less than 5 mil, where it spans over the windows. I think what this really shows is if you get the geometry right, as we have this kind of domed shape here, we have a structure which doesn't really have a traditional structure in terms of ribs and beams. It just has the panels, which are all leaning against each other and then screwed together at the joints to create this this shell over the chapel. And then there's some finished images here. It was actually rendered on the inside. And from the outside as well, yes, it's just in it's a, well, let's say, modestly scaled. It's the end of terrace in a suburban part of Canterbury, but quite an interesting project nevertheless. From then we moved on to again with the same design team, look at a slightly larger chapel. This one is in London, a very different setting, and this one is actually built as an extension to a heritage building, a listed building in quite a noisy part of West London. And the chapel that we were working on is the shape you can see on the right hand side, and then the white to the left is the existing building. I mentioned it was a fairly noisy site. Loads of planes flying overhead and sirens going out past the street outside. And what we wanted was to create a kind of a much more quieter, reflective space inside. And we have what we called our box within a box. So we have an outer structure, which is doing one thing, and then we've got an internal structure, which is doing another. I'll come on to some more images of this and explain that better. But here's some architectural sections, long section, short section, kind of showing how it relates to the adjacent structures. And you can see here we've got an external and an internal structure. The external here we formed using CLT panels, and then the internal structure was a combination of glulam and just conventional sawn softwood, and create this kind of miniature cathedral, if you like, where you can be quite expressive on the inside and doing what the space needed to do through the workshops with the client, whereas we have on the outside our CLT structure, which is doing something different and needs to fit in with a kind of heritage streetscape outside. You can see that something interesting is going on there, but you're not quite sure until you go inside. So that was an interesting kind of process, and learning again a few years ago now, but really getting into what we could do with these cross-laminated timber panels. And then moving on to this third in the series of these chapels. This is an early architectural model, and again a very different setting. This is in a town called Stroud, and not the same kind of urban setting as the London one at all. And yeah, the idea was to continue looking at how to use CLT to create these special structures, and some quite complex geometry, as you'll see there. Now, so why is CLT so interesting? I mentioned before about this difference between a kind of a framed structure where you build your structure and then clad it and put your finishes on that, to this idea of using the actual skin itself as the structure. Now this is taken from the York Railway Museum. On the left-hand side is one of the early versions of a train carriage, and then on the right-hand side is a more contemporary one. And you can see one looks to me relatively lightweight, and the other one is relatively heavy. So the one on the left there has a traditional kind of chassis with a carriage kind of built on top, where the one on the right acts like a tube, so that it's a structural skin, and as a result is a more lightweight and fast moving modern train. So it's monocoque construction, and yeah, it's used in cars as well, where the actual skin is the structure. This was not one of my structures, but a bit of an inspiration when we started working on the Stroud Chapel. It's actually in Switzerland. I think it was actually built as a temporary chapel. I believe it's still there many years later. But you can kind of see here this idea of using the geometry to create the stiffness. I think all these panels are 60 millimeters thick kind of CLT, and the way that this has been kind of folded together with this kind of almost like origami shape generates not only vertical but also lateral stiffness. So that was just seemed like a great way of building. So not just buildings, not just train carriages, but also if you look at musical instruments, again something quite thin shell, but with some curvature in it, creates not only efficient structures but also ones which sound very different, and the acoustics which are set up in these spaces and the relationship between the structural performance and the kind of acoustic performance, which is obviously very important in all sorts of buildings, but especially in religious buildings. So these were some of the thoughts in our head as we began this exercise with Nick, and I think the ability for engineers to sketch as not only the early ideas are exchanged with the architect, but also the latter days as well, when you're looking at doing the details. I think this idea to communicate different design options using sketches and experience and approximate rules of thumb is a very useful thing. And here's some early sketches that we were exchanging with Nick to explore that at the early stages. What do these forms actually mean structurally as well as architecturally? Yes, not only to sketch, but to actually make models ourselves, and look at these kind of folded plate structure and see what it means like in actual 3D. scaling it up to 1 in 10. And I think these are not only tell us quite a lot about how something can be put together, but whilst it's not a kind of formal structural model, you can generate quite a lot of intuitive feel about how something's actually working. And we could feel as soon as we were folding this arched shape, something was happening where it was becoming very kind of rigid and felt very sturdy as we were building it. And then, of course, moving into 3D and to try and understand this structural system that we had. If you look at it in 2D, you initially think, right, we have a portal, and we all know about portals, how to design them. But in actual fact, if you think about it in 3D and try to explore those load paths, you see that there's these other systems at play here, which are actually which are stiffer, will therefore attract kind of more load, and are also more efficient. In the case of this, we have an arch which is set up between the altar end and the congregation end, as well as a shorter span arch, but the shorter span arch doesn't have as quite a stiffer springing point and therefore doesn't attract quite the same amount of load. Loads of complex 3D FE analysis went in to explore this further, and we're always very aware of this idea that, you know, what to say, rubbish in, rubbish out. So you always have to treat these models with a healthy dose of skepticism. But I think with this and also the previous forms we were looking at, you know, we can do our own hand analysis on an arched or a catenary to understand what we think the forces are in the elements and what we think how much it moves. We can use this to kind of cross-reference our models and see whether we're converging on something which seems about right. So yeah, very complex, very complicated structure. We've got an external kind of glulam frame. Internally, you see the CLT panels. That was the expression to the internal kind of surface, and that in itself is a structure. However, what we found was that the forces that were generated by the joints were quite large, and also there was some areas where it was kind of relatively flexible. And when we created this glulam grillage on top, there was a lot of additional stiffness, and also really helped out the joints. Alongside that, loads of hand sketches to look at the different jointing patterns. And then onto the construction. And it was something we were a little bit, yes, it was a kind of question as we were developing. It was just how to build it. And I think what's true with all of these is you can't really design these without actually a really close engagement with the contractor and the fabricator and the people who are putting it up. And that was certainly the case here. That we found the shapes went together. They could only really go together in a particular way. And in a way, it was like a 3D jigsaw puzzle, which could only be built in one way. But the question was how to build the roof. The walls, they went up, and we built the kind of single story ancillary spaces around the edge first, and then they acted like a prop to these double height walls as they were lifted up. So there was no need to then put additional props to mark the internal surfaces and kind of constrain the construction inside the space. And there was various ideas of how to build a roof from the contracting teams who are in the running to build this. And there was quite a lot of expense which was associated with a kind of a birdcage scaffold which would go inside to create temporary props. whilst the roof was being erected. However, ultimately, we ended up with this idea here, where we created a series of, I think it was 3 temporary arches by putting up the glulam first, with 3 props down either side, temporary props down either side, whilst this was being built onto the ancillary spaces roof down below, and that created our kind of 3D geometry, if you like, and allowed then roof panels to be lifted up inside, and they were actually screwed down from above through these 300 deep glulam members that you can see in this image. And yeah, very talented team of site erectors put it together, and we were yeah, it was very impressive. And this is the final image you can see here of the space that was created, and in a way we think kind of reminiscent of the traditional kind of vaulted kind of stone churches and cathedrals you see, but built in this kind of contemporary way with cross-laminated timber panels, and a very distinctive shape from the outside too. So looking ahead then, here we are in New Zealand, and I've been getting around and trying to meet as many and see as many people and things as possible, and it's truly impressive, I think, to see the this kind of history of and tradition of designing and building with timber here, and not only building but also kind of fabricating. That's kind of quite unique, I think. Well, I was coming from the UK, where we do make quite a lot of our own panels, but also import a lot from abroad, and much more of a self-reliance here, it seems to, and this onshore fabrication capability that we have is seems to me to be a great thing when it comes to these kind of structures. And I can see there's been, especially over the last decade, a real kind of interest in mass timber and this question of how it performs seismically, and some pretty amazing things being conceived. So I kind of see this kind of innovation and interesting craftsmanship, and being able to do things ourselves here from within our borders as being a real great strength of the timber design and construction industry here in New Zealand. And I think that'll stand us in really good stead, I think, as we look ahead to economic recovery, and not only doing some very impressive kind of one-off special structures, but also as we apply that to much more kind of everyday kind of structures, and can really make probably much more of an impact on their carbon footprint and overall efficiency of our construction sector. So that's probably a good point at which to stop talking, and I'll be very interested in understanding from everyone here any thoughts and reflections you might have. Thank you.
Thank you, Peter. That was a very great presentation. I really liked the different structures you have selected, but also the analogy reference to musical instruments or the carriage and so on. And I think timber really leans it's well to architectural thinking or shapes, which, yes, you can do with other materials, but you can also expose them nicely and they look quite good. So yeah, really great presentations. I hope we're gonna see more shells and grid shells and folded structures in New Zealand moving forward. So we have a question here about the actual roofing. So what's your take on how can you clad such a folded roof plate, allowing for rainwater collection and controlled movements of the hip joints? Any thoughts on that? And I think the picture you're showing probably answers a little bit.
Yeah, yeah. It's good. It's a very good question. I think there are all the different geometrical shapes, how to clad them and how to get the rainwater off efficiently is a really good thing to think about. In this particular instance, there was actually a secondary roof that went on top of I-joists that was then created a secondary surface over the top, which was waterproofed with, in this case, I think it was lead was used at the kind of valleys you can see there, and timber shingles between to provide the rainwater runoff into those gullies, which you can see. So this, in terms of hip movements, it's not actually not actually working as a portal shed. It's working as an arch, which kind of spans about 20 meters from the altar end to the congregation end. So there's not that same level of movement that you might get in the portal shed, for instance. It's actually not a lot of movement at all. So yeah, that didn't really present the same amount of issue as it would have done with a more flexible system. But certainly there are shapes I've seen and buildings I've read about and visited where that has been much more of an issue. The amount of movement anticipated.
Thank you. There's a probably more open discussion type question, but I still gonna ask it. What's your take on what's holding back progress on timber projects at the moment? What's your take, and perhaps also, coming from overseas a bit more recently, but what do you think is holding us back in New Zealand at the moment?
Well, I think maybe the same thing which is holding back any other type of building, money. And there are new buildings being built, but probably less of them than in the past. There's perhaps a perception around risk and cost and how integrated the industry is. And I think a lot of that is perhaps a perception based on historic things rather than where we're at the moment. And what I see is much more integrated design and construction fabrication processes than what I've heard about in the past. So I think that's a good thing for us as we a design team can be a design and construction team can be very fragmented, and everyone is doing their little bit. But ultimately the client is looking for a kind of much more holistic kind of proposal. So I think those kind of things, as we kind of pull the supply chain and also the design aspects which go along with that together, especially at the latter stage of the project, but also at the early stage, all of that is a good thing in terms of reducing the risk, I think, to the client. It's possibly, there's probably a lot more choice now. I think there's more fabricators and people offering kind of products than there has been in the past, and I think we need to perhaps work to get those kind of messages out there that it's really improved. So I don't know, as you tell me, Daniel, you've been here for longer than I have. You've probably got much more of a kind of perspective on it than I do.
Well, no, I agree with you. It's generally the economy is a bit slower than it used to be. In terms of timber, I think it's this bit of a pendulum effect. We had very little timber buildings, and there was a bit of a boom for a while. More architects, developers were interested in timber, and at the moment, it kind of perhaps different government direction, different economy. It has swung a little bit back again, but I'm very much convinced it's coming back. And with people seeing what can be done, and your presentation is a good contribution in terms of quite innovative or different shape structures. There's definitely, I think, more coming again. But what we hear from our Timber Design Society perspective is still this perceived risk fire being one. Obviously, with the Timber Limited guideline, or the Yellow Book as they call it, they have provided some consistency. Obviously, pricing or costing is still a bit of a headache, where QSs try their best, but then still at a premium. Either the QS or the construction company adds a premium to the costing. And I think once we are a bit more confident what works and what doesn't, we will definitely get there. So I'm surely still positive, and I think we keep on pushing. And there's more suppliers in the market. There's more designers, and yeah, we're learning fast, and we're all trying to implement this knowledge into new timber building. Peter, there's another question about a folded structure here in Christchurch. Are you aware of the Mount Pleasant Community Centre down here? And if so, do you have any thoughts or comments on that structure?
Yes, is it the Chris Smoller? Yes, I think yes. I've seen images of it, and it looks really impressive. And obviously there's some of these kind of folded plate origami ideas there, to create the structural stiffness rather than just putting a big beam across. Job done. You know, they've kind of looked at how to do that a bit more efficiently and elegantly. And what I really like about it is the kind of, we use what's available to us, right? Which is, I think it's LVL, a lot of LVL there. And you know, if you did that building in, I don't know, South America or Finland, you'd probably be using different products, perhaps, for what you got available. And so I think it's, yes, it's a really good kind of interpretation of, or you know, version of that kind of structure in a kind of New Zealand kind of context. And I'd love to go and visit it at some point. It's exactly the kind of thing which I've always found so fascinating.
Perfect. So you've almost reached 1 p.m. So I have one question from my end, Peter. You did mention before that most of the structure are relatively stiff, which can be a good thing. But then when you think about seismic,
Mm.
in order to get dissipation, you typically need some sort of movement. So being in a seismic country now, what's your first thought about grid shells or folded plate structures and seismic performance?
Yeah, good question. Well, I think generally speaking, I mean, the idea of hybrid construction is very, very attractive, isn't it? And the lightweight nature of timber for gravity, and some steel for the lateral, and using the inherent kind of ductility of and efficiency and tension of the two combined is really, yeah, it's pretty powerful. And certainly as we're looking ahead as to more kind of pragmatic way of doing everyday buildings to really make an impact, I think that's very, very interesting area. Going particularly to these kind of structures. I mean, they are 1 to 2 story timber frame structures, and so I think they would perform very well. Historically, I don't think the big issues have been with low-rise timber construction here, and I think timber, as well as being kind of lightweight, get all this nice damping as things do move. And yeah, when we've looked at kind of timber staircases and the dynamic performance of those, it's been an area of mine. And I think sometimes the prediction is more conservative than the reality. So yeah, I think, don't know if that was directly answering your kind of question, but I certainly think they have their place to play here, and they wouldn't need that much tweaking, I don't think, to get them to perform in most parts of the country.
Perfect, thank you. And there's one last question which just came in I would like to ask you, and it's about, would you agree that essentially most timber buildings in New Zealand currently are bespoke, and we're still a long way of having standard designs or standard connections? What's your answer to that?
Yes, there is a lot of bespoke kind of buildings there, and I think, I mean, they're both important in terms of developing and learning and research and development and those kind of things, but they can mean that can be a bit painful to deliver sometimes, because there's so much time taken by designing and then viewing all these kind of bespoke components. But there are, I think, more and more proprietary off-the-shelf systems available to us. We can import or make our own kind of connections pretty effectively. And I know there are also building systems, the LVL portal sheds I've seen, for instance, where, or just call them a shed is to play them down a bit. They're kind of large kind of warehouse structures. I can see there's a convergence there on a standard way of kind of connecting, and I can also see that seems to be a doing good things in terms of cost and speed of construction. So I think historically there has been a lot of bespoke stuff, and that will always have its part. But I think more and more we should be looking to standardize where we can. We can't be reinventing the wheel every time.
Yeah, no, I agree with that comment. And someone else kind of also joined in saying, yes, there's some standard connections out there, and from our end, we are aware of this fact, and I think we are working to standardize the way we do. But I think every engineer still has a bit of their own opinion what works best, but also suppliers. From my experience, different suppliers have different favorites. So I probably also I put the question back out there, like maybe it's worse for the suppliers to also sit together and discuss what works best, because if we can grow the cake all together, then we all get bigger slices out of it. Right. I think we leave it at that. Peter, thank you very much. There were some other comments which I haven't read because they were comments, but some of them are like really beautiful structures, and hopefully we see some more of them in New Zealand. So an encouragement for you and your team and all other designers and timber engineers out there. And with that, I think I say goodbye to everyone, and hopefully all have a good Easter break, and stay dry and safe out there. Thank you very much, Peter. Thank you, everyone, and goodbye.